let's recall the arc length formula that we saw for curves in the plane. We actually saw this two different ways, but let's go through it again. So the idea here to start off with is I have some curve, and right now I'm thinking of it as a y equals f of x. And I want to find out how long the curve is between A and B. I want to measure that distance. So I start off and I imagine chopping up my x-axis so that I can chop up my curve into little parts. And then I imagine actually measuring the distance in a straight line between the endpoints. Kind of imagining measuring these little straight line distances to approximate the length of my function between A and B. And if I zoom in on one of those line segments, I could imagine that as a little part of the function that looks like that. And to find that distance, I don't even have to approximate. I could just find the little change in x from left to right and the little change in y from bottom to top, and then use the Pythagorean theorem. This line segment's length is the square root of delta x squared plus delta y squared. And I could do that for each line segment, which then I could add together to approximate the total length. Add up a whole bunch of delta x squareds and delta y squareds. And really, I'm thinking about a delta x and a delta y on the kth subinterval, right? All right. And then we always ask, okay, how can I make this approximation better? Well, the idea is I need to take more and more little line segments in there, right? I need to let the intervals get smaller and the number of line segments get bigger. So I'm thinking about this as a sum from 1 to n. I need to let n get bigger and bigger and bigger. And what we're really doing is taking a limit as n approaches infinity. And this is starting me to think about a Riemann sum. Right, one of those sums that looks like this, right? That defines my definite integral. And then I look at this and say, well, this would be a function. It just doesn't have the delta x I want or the delta x sub k on the outside, right? It's not really a Riemann sum yet. But it has like all the right parts. And so what we did when we established the arc length formulas that we know back in Calc 2 is we rearranged that formula just a little bit. And there was actually two different ways to do it. The first way was to rewrite the inside of this square root so that I had a delta x squared k over delta x squared k and delta y squared over delta x squared. And just for a moment, under the square root, I multiplied everything by delta x sub k squared. And of course, if I distribute that through, it cancels off what's on the bottom. And I said just for a moment, because my actual goal in doing that was to be able to take the square root of this and write it on the outside. All right, so now I need to examine what's still under the radical, but I have the delta x sub k I was looking for to make this a Riemann sum. Well, delta x sub k squared over delta x sub k squared is 1 plus delta y squared sub k over delta xk, so I can think about that as all being squared. All right, so now I imagine taking a limit as n approaches infinity, which is making these widths get smaller and smaller and smaller. So we wrote that as an arc length formula. That was the integral from a to b of the square root of 1 plus. And when I think about delta y over delta x, as delta x goes to 0, that's the first derivative. So that's dy dx squared, and then this delta x sub k, that's my dx. And so that was the first arc length formula you saw. The integral from a to b of the square root of 1 plus the derivative squared dx. And then later on in the course, we rethought that just a little bit. still starting at this moment, we rethought, instead of having a curve, y equals f of x, what if I had a parametric curve? X equals x of t, y equals y of t, right? Instead of thinking about this as a function, maybe it's a parametric object, right? And I have two functions, one for x, one for y. Well, I can do that same kind of trick on the inside of my radical. It's just instead of dividing by delta x sub k, I could imagine dividing by a change in t squared. And just like last time, I want to multiply by what I just divided by, take the square root and write it on the outside. And now the limit as n approaches infinity. My intervals get smaller and smaller, which means my parameter intervals also have to get smaller and smaller. So this becomes this definite integral. And then this was a parametric arc length formula. So for a parametric curve, okay, so having gone through that derivation again, now we want to live in 3 space. And the first idea doesn't really apply, right? Because in 3 space, my curve is either given by a set of parametric equations or a vector equation that has those parametric equations as its components. So I could think about this as an x of t I plus y of t j plus z of t k. And then the approach is the same. I want to measure the length of the curve on a certain interval when t is between a and b. Maybe I start here and end there. I chop the line segment up using a little partition of the parameter interval. And then I think about a straight line distance on every subinterval. Well, if I think about it, that would just be a 3-dimensional distance formula problem, delta x squared plus delta y squared plus delta z squared. And so the same idea works, all of the derivation works, I just need a dz dt term. So in 3 space, our arc length formula looks nearly the same with just that one more term. So let r of t generate a curve in space. The arc length of that curve is the definite integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared dt. There's something even better that we can understand now. This was my vector function, this is its arc length, but dx dt, dy dt, and dz dt, those are the components of dr dt, the velocity vector. And I recognize this square root as a property of this velocity vector. If we were in a classroom right now, I'd just pause and wait for someone to say it. But if I take the components of a vector and square them, add them together and take a square root, that's the magnitude of that vector. This expression that's sitting right here is the magnitude of the velocity vector. So for a curve in space, the arc length from A to B, or better said, the arc length when t is between A and B, is the magnitude of velocity dt. Another way to think about the magnitude of velocity is speed. And now this equation makes perfect sense. We're adding up a bunch of speeds times change in time. Well, a speed times a change in time is a distance. The arc length formula we learned from parametric equations in Calc 2 is really the same thing. This is an equation for speed in the plane. I'm always very happy when we get right here. Arc length, the integral from a to b, speed dt. Next video, we'll do an example of finding an arc length.